we're going to be talking about how fast physical optics enables the modelling and design of metagrating structures. Now, fast physical optics is the name we have given to the technology implemented in the software VirtualLab Fusion, and a key aspect of that technology is what we call connecting field solvers, with the objective in mind of being able to simulate complex optical systems made up of many different components with different characteristics. What we do is we select different solvers for each of those different components, and then we bring them together, we connect them in a seamless, non-sequential way to, in effect, provide a Maxwell solver for the whole system. Today, we're, of course, going to concentrate on metagratings, and circling back to that from this general introduction of what the software does, the first thing I would like to mention is the solver that we use in general to simulate metagrating structures, and that's going to be the Fourier model method, FMM for short, which you might also know as rigorous coupled wave analysis, RCWA. Both terms are used in the literature and in the community. The first example that we're going to tackle today is the design of a blazed metagrating. And we're going to be using the scientific publication, the scientific paper that you can see cited on screen as a reference. The citation will also be, of course, in the material that we will send to you after the webinar. So if you're interested, do take a look. But the gist of the matter is that we want to design a metagrating structure that replicates the behavior of a traditional blazed grating. Now, in the blazed grating, what we vary in that typical blazed shape is the height profile of the structure, the relief of the structure. In the case of the metagrating, we want to replicate that behavior or get an equivalent behavior, a comparable behavior of the structure, but this time by varying not the relief, not the profile, but the sizes and positions of a given arrangement of pillars. The pillars are all going to have the same height, but we're going to change the lateral size of their base. The base is going to be square, and we're going to produce an arrangement of differently sized pillars within a period of our structure. And with this strategy, we want to replicate that behavior of the blazed grating. So that's the function that we want to fulfill with our design. The first step is to configure an initial system that we can then optimize further with parametric optimization. And in order to find this initial system, or in order to find a suitable suggestion for this initial system, we're going to perform a preliminary investigation. We're going to start by defining a pillar grating. Note, not a metagrating yet, but a pillar grating. That is, we're going to have a single pillar per period, and as such, all the pillars in the structure are going to be exactly the same for the time being, because we are going to have a periodic replication of that fundamental period. Then we're going to perform a simulation of this structure with a plane wave as our input field, and we're going to read the phase of the field after it is propagated through a pillar grating defined in this way. And then we're going to repeat the same process again for a pillar grating where all the pillars are exactly the same to each other, but where these pillars have a different size from those of the previous simulation. And once again, we're going to read the resulting phase. And we repeat this process iteratively, which will yield a plot of the phase as a function of the pillar size. And for this, we have used the parameter run feature, a tool that allows us to perform parameter sweeps in the system, and which provides different options to display the results graphically. We have adjusted the resulting linear plots slightly to show the efficiency of the order alongside the curve that represents the phase, to ensure that we maintain a minimum efficiency threshold throughout, the range of interest. So said very roughly, it doesn't matter how the phase behaves if we have no actual field to exhibit that phase. So that's why we also show the efficiency alongside the phase to ensure that we have energy to fulfill the function we want to fulfill. And now comes the assumption. Since we want the phase distribution of the field after it is propagated through our metagrating to exhibit a blazed profile, we're going to construct the period of the metagrating by assuming a direct relationship between the lateral size of a pillar and the phase it produces, according to the plot we just saw. We arrange the differently sized pillars along a single period according to the blazed phase profile we want to obtain. And this assumption is, of course, not perfect, but it is quite reasonable in order to construct an initial system that we can then optimize further later. And we see now on screen the structure that results from this process, the initial system, the initial metagrating that we can then optimize further. And as a first test, to check if our assumption makes sense, we can run the simulation to look at the face of the field behind the structure. In the near field, directly behind the structure, it is not so clear because there are evanescent fields that smear the result. But if we allow the field to propagate a little bit, if we allow the evanescent fields to ebb away slightly, we can clearly discern that the assumption holds out and that we have produced a structure that fulfills the desired function. So now the last step, and the only thing that remains, is a parametric optimization. What we want to achieve with this is to maximize the efficiency of the working order, that would be the first order, for two orthogonal polarization states, in order to make the situation polarization independent or as polarization independent as possible. And we're going to use a polarization analyzer to that end in order to produce a merit function for this optimization process. And the polarization analyzer is an off-the-shelf analyzer that is provided with this type of system. Here we can see how the curve of the average efficiency for both polarizations has progressed throughout the optimization process. And we can also take a look at the optimized structure, and we can see slight differences with the initial system that we constructed in the previous step. In the second and last example of the day, we're going to follow a similar sequence of steps, but with some variations which I think are going to be of interest. And this time we want to create a 3x3 beam splitting metagrating. And this means that this time the periodicity is going to be 2D. So before, in the previous example, we had a 1D periodic metagrating. Here, the arrangement is going to vary in 2D, and it's going to be replicated periodically in 2D as well. Before, in the previous example, we started from the knowledge that we wanted to generate a blazed-like phase profile behind the structure. But this time, we're going to use the iterative Fourier transform algorithm to design the pixelated phase distribution that we need to generate behind our beam splitter. The IFTA optimization is also a feature included in VirtualLab Fusion. And for a beam splitter, for the design of a beam splitter, it actually provides a wizard that takes you through the different steps of setting up and performing the design. But we're not going to focus on this part to keep things short and concentrated on metagratings. We're going to jump directly to one of the many possible phase distributions that are generated with this IFTA design algorithm. And that's what we can say here. Once we have this desired phase, We repeat the same process as before. With a parameter run, we perform a preliminary analysis of the unit cell. And we could, as before, do things manually read the desired phase value and the corresponding pillar diameter from the result of the IFTA design and from this preliminary analysis of the unit cell. But that will be time consuming and a little bit boring and painstaking work. So we can also automatize the process with a C# module, which is one of many programmable features of VirtualLab Fusion. And we're going to use one module first to invert this function in the selected range. And of course, we need to ensure that the range we have selected provides an invertible function. And then we have another module that reads the corresponding phase values from the IFTA result and assigns the pillar diameter to each of them and generates a data object that we can directly import into the metagrating structure. And so we didn't have to do any of these steps manually. It was all automatized using programmable capabilities in the software. Finally, we would of course perform the parametric optimization of the system, of this initial system, and we're going to use an analyzer that was again programmed as a custom feature for this example. And this programmable analyzer yields the uniformity error, among other things, taking into account the orders of interest, the working orders. This is the merit function that we want to, the key merit function that we want to optimize in this case. We want to achieve as high uniformity as possible. And finally, on screen right now, we can see the initial system with the corresponding results and then the optimized system with the corresponding results. And we see how the uniformity has in fact improved as a result of this optimization process, as we hoped and expected. That's it for the presentation. Let's move on to the Q&A. Thank you for listening.